Can see it.
All right. Thank you very much, Hadi,
You're welcome.
for this opportunity. And actually, some of the attributes, actually, you read from the bio I gave you, but I need to be careful here. There are plenty of people here knows everything better than me. So saying expert or broad knowledge, I should be a bit conservative with that. But anyway, that's a great opportunity to talk a little bit about what I am doing in terms of research. So I will talk about some problems in assembly line balancing, and we decided to deal with these difficult problems using some metaheuristics. I explain why, and actually the time that I was preparing for this talk, I found that Alison is doing working on similar problems, so that was, you know, the evidence that I received already for this presentation. So everything kind of started from Henry Ford's assembly lines line system for mass production. And the idea of assembly lines is for a kind of production system, which is considered as a flow orientation. For a while, that was the best idea in terms of mass production. But as time goes on, and even right now, there is a great tendency for product variability. And also we have shorter life cycles of products and services. So in response to relatively low demand production systems, instead of a mass production, in terms of considering a particular product and just different versions of the final products, it's a bit uneconomical to create new assembly lines to cover any variation of the product. So the idea is to have one assembly line, but which is capable of producing several versions of the same product. So the key terminology here is assembly line. And as I said, through my preparation for today, I found Alison and I watched his presentation. It's really fantastic presentation. I think I was going to say that's a prerequisite, but that's true. And I'll explain that our approach is a bit different from Alison. So Alison, I liked his presentation and the way he's working on mathematical modeling side. But for us, our tendency is to solve larger problems. So definitely mathematical programming is not going to respond to that request. Sure. Okay. So in terms of assembly line balancing, let's see what components do we have to establish a problem instance. So we have a product, and the product is subdivided into tasks, operations, or jobs. They are going to be used similarly. So we have a set of tasks and jobs, and we want to assign them to a set of workstations or machines or stations. The point is the jobs have precedence order, and some jobs could not be completed without some jobs completed before them. Also, for each job, we have processing time. So one of the assumptions is all the stations are going to be similar in terms of they can do all the jobs. And that's why we don't, for this problem today, we are going to consider all the stations are going to be capable of doing all the jobs, and the processing time is going to be the same. So processing time is independent of a particular workstation. So the aim is, as many optimization problems, we want to fully utilize resources. Definitely, if we can bring down cost or time of production, also, we would like to utilize as much as possible of the workstations that we have. And in the literature, you see equivalently people solve the same problem with the objective of maximizing throughput or minimizing cycle time or minimizing number of stations. So some sort of optimization is going to happen there. So I highlighted cycle time. Cycle time is a very important concept in all production systems and manufacturing. And actually, that's going to be the time that a complete product is going to be produced, right? So, and at the same time, we have a similar concept for each workstation. So every workstation is going to be allocated several jobs, and that cycle time is going to be the amount of time that a workstation is going to spend to complete all assigned jobs. So to give a toy example, let's say we have a product, and this product has subdivided into 6 jobs. Each job is going to, the numbers inside parentheses is the amount of time necessary for the completion of that job in time unit. And actually, this directed graph shows the precedence order as well. So A should be completed before B and C, and A and B should be completed before D. Finally, D and E should be completed before F. So the table on the right-hand side shows the task, the amount of processing time, and the precedence order. And the table, the second table shows a feasible solution. And for this feasible solution, so we have 3 stations, A and C assigned to station 1, B, D assigned to station 2, and finally F to station 3. And you see that for this problem, actually, we assume that the cycle time is 20. So the amount of time for each station should not be more than 20. And by this feasible solution, we see that each station is going to be engaged 18, 20, and 6 minutes, and there are some idle time, right? So one of the aims that we have, we want to minimize the idle time of workstations. We want to utilize them as much as possible. So this is a kind of simple assembly line balancing problem. But I thought that this is a good example to see what we are saying, what we mean when we are talking about the jobs, about the precedence order, about the processing time, and the kind of solutions. And you see that solutions are going to be permutations of jobs, but they are going to be assigned and allocated to workstations so that first they're going to obey precedence order. At the same time, they're going to optimize some objective function. So assembly line balancing problem has several versions or categories. If there's only a single product, we are dealing with simple assembly line balancing problem, or SALBP, which is the perfect model for mass production of a single product. But as I said, considering the tendency of the variability in final products, it's possible we consider mixed model assembly line balancing problem, or abbreviate as MMALBP. So in this case, we are going to have a single assembly line balancing, single assembly line, but several versions of the same product are going to be assembled. Also, assembly lines could be distinguished based on the physical setting of the line. Could be straight. Generally, when nothing mentioned, it's supposed that the assembly line is straight. It could be U-shaped. It could be parallel or two-sided. Also, based on the objective function, we have 2 main categories, type 1 and type 2. Actually, there are some other types, but These are, I would say, the most frequent types you would see in the literature. With type 1, the idea is to minimize the number of workstations given a cycle time. And with type 2, the idea is to minimize the cycle time for a pre-specified number of workstations. So these are kind of the more frequent types of assembly line balancing problem. So I mentioned about processing time, and I said that's going to be independent of machines. There are other concepts considered in assembly line balancing problem, which is called setup times. Setup times, just imagine that for different types of jobs on a single machine, sometimes it's necessary to do some tool change or even some operator changes. Some sorts of changes are going to be necessary. So generally, the setup times are neglected, and the reason is it is negligible considering the cycle time. But as we are getting towards shorter and shorter cycle times, neglecting setup times is not going to be possible anymore. So another layer of complication is to find the permutation of jobs assigned to workstations, not only considering the processing time, to consider the something called forward setup time. When one job goes, we want to do the next job, we need to do some setup and preparation. So in this talk, I'm going to look at mixed model assembly line balancing problem. So one single line, several models of the same product with setup times, and it's going to be type 2. It means we are given the number of stations, and we want to minimize the cycle time. And from the final solution, we can find the optimal cycle time, the workload of each station, and the optimal allocation of jobs or operations to workstations. So the problem is going to be NP hard, and it's a difficult problem to solve. That's why we decided to work on metaheuristic part until we are waiting someone shows that NP is P. So to have an instance of this problem, we have several parameters. Capital N is going to be the number of jobs or tasks. Capital M for the number of models in the problem. W is going to be number of workstations. And the precedences are shown by PIG, or just the an ordered pair. And setup precedence is going to be shown by P. The processing time of each job in each model is going to be shown by TIM, and F with indices IJM is for model M. To move from job I to J, it's going to be the amount of setup time. So as always, the first attempt is to establish a mixed integer programming problem. And here is the list of variables. C, the cycle time, is going to be a continuous variable. We have some binary variables. Y is responsible for allocating jobs to machines. W is for taking care of the precedence. And X is going to be if job J is going to immediately follow I for a particular model on machine S. So because the problem is type 2, the objective is to minimize the cycle time. And minimizing cycle time is equivalent to minimizing maximum cycle time of each station. So for all the stations, there are going to be a set of jobs allocated. So for that station, we can find station load and station completion time. And if the max of cycle time of a station is going to be minimized, that's equivalent to minimize the cycle time itself. And we have a set of constraints. These two constraints here, one is making sure that all the jobs are going to be allocated. The second constraint is going to make sure that the precedence of allocations are respected. So Alison did some interesting job on making this constraint a bit more computationally efficient. So I'm using the old constraint, that old kind of representation of the constraint, because generally different representation of these constraints are going to be the same. So we have a set of more constraints, and this set of constraints are going to make sure that the precedents are respected when we are allocating jobs to machines. So I'm not going to go through all of them. It's a bit time consuming. Similarly, the order of jobs and workstations, respecting each model. And also we need to bring the idea of processing time, not only the, the setup time, not only the processing time. So for solving the problem, we have a mixed integer representation of the problem. And actually later in the numerical results section, I'll show that even using the state-of-the-art Groby software package is not capable of solving, or is capable of solving only small problems. So there is a necessity, and actually there is a huge literature of using metaheuristic to solve this problem. So I'm going to mainly look at a version of simulated annealing we adopted to solve this problem. And for the sake of comparison, I'll represent a version of Colony Optimization. And we compare all of them with what we achieved from using Groby optimization software. So I think everyone knows simulated annealing. So there are a couple of factors we need to decide when we are developing simulated annealing for a particular problem. For example, the initial temperature, the cooling strategy or schedule, and some internal parameters. So this is the kind of representation of simulated annealing. I'm going to go through some parts because I think they are the changes we made to make simulated annealing works for solving this problem. And the main idea is that it's not that difficult to make permutations using simulated annealing, but we need permutations that they're going to respect precedence order of jobs, and at the same time considering processing time and setup time. So we initialize a couple of permutations. And actually, so the algorithm starts with the instance of the problem with initial time, with time initial temperature, the time limit. So the stopping criterion for this algorithm is going to be time, and number of internal iterations. So the second box is kind of conventional simulated annealing that is generally used for combinatorial optimization problems. So for a given permutation, we have swap operations that kind of neighborhood search, changes just two jobs, and checks that if there is any improvement in the objective function or not. And based on, and that's the nature of simulated annealing, sometimes we let the algorithm to go uphill rather than always downhill. So when we have a permutation, let's say PIB, we search that if we can update it a bit more, and then we apply something called beta sampling. So beta sampling, I'll explain beta sampling more, but the idea is we needed to bring more diversification to let the algorithm to search a bit more in the space of permutations. So even after applying beta sampling, we generate a random number, R, and based on where R is going to sitting, we may insert a brand new permutation, or we apply another beta sampling, or we apply M swaps. Rather than just one swap, we do, and M is going to be a given parameter. So with this, we try to bring more diversification to the algorithm. So the output of this simulated annealing is going to be a permutation, hopefully with some good objective function value, but it's not necessarily going to follow the precedence order. So what we do, actually, I explain the beta sampling, which is quite simple. So instead of just one swap, so inside the permutation, we choose a substring or subsequence and put it to the end, right? So, and we select B is going to be a given number, so that's going to determine the substring, and R is going to be a random number. So we choose a substring and we put it to the end. So as I was telling, the output of simulated annealing is going to be a permutation, but the permutation is not necessarily a feasible solution because we have not talked about the precedence order yet. But they are going to be good permutations because we chose permutations that they have better objective functions. So the output of the simulated annealing part is going to be inserted into another heuristic algorithm, which gets a permutation and converts it into a feasible permutation. So this algorithm have a couple of settings. We have the idea of weighting list here. So when we have a permutation, we go through the permutation elements one by one, and each is going to be a job. And we check that if the precedence is okay, if all the predecessors already completed or not. If it's okay, so we allocate it to the best possible workstation. I'll explain what that means. Otherwise, we put it in a waiting list, and it's going to wait till all its predecessors should be completed. And by this procedure, we can convert a particular permutation into a feasible permutation that satisfies the precedence order. So the main part of this algorithm is to allocate a particular job to the best station. And how it is going to happen, the idea is here. So for permutations, we have T max, that's the maximum amount of time, or the job with the maximum amount of processing time. And for each job, we have its processing time. So if processing time of the job is less than half of the max of permutation time, we allocate it to the station that satisfies in this condition. And what it says, I pictorially, visually represent the meaning of this in the next slide. But here, we consider all possible stations, their current cycle time based on the jobs allocated, and the processing time and the setup time, and we divide it by number of jobs assigned to that station. So otherwise, if TIM is greater than half of the max permutation time, it means that that's a job needs a lot of time, and we try to allocate it to a station with less operations allocated. So this way, what's going to happen? We kind of try to add jobs with smaller processing time to pack them on the stations that they already have capacities, and we allocate jobs with larger processing time to stations that they are kind of quiet. So this is the idea behind allocating jobs to stations. Let's say that the row is a permutation of operations, and we have 5 given stations, so we can allocate first 5 jobs to each station. And now the question is where we are going to assign operation 6. So we assign operation 6 to a station that operation 6 plus the forward setup time is going to be less than others, and it happens to be at station 3. So this worked really well in solving this problem, and actually we checked. This is kind of novel approach in this area when we are dealing with assembly line balancing problem with setup times. Also, for the sake of comparison, we decided to have a version of Colony Optimisation, so another nature-inspired algorithm. And the idea is we wanted to get permutations both out of simulated annealing and from Colony Optimisation. Then the permutation is going to be fed into the best allocation algorithm that I just explained. So again, here an instance of the problem with max time and number of ants in the population with the parameter Q0 is considered for ACS. So the pheromones are going to be initialized. For example, they can initialize uniformly. Then NS, the number of ants in the population, we're going to create several ants or several solutions. And these solutions are going to be evaluated against the objective function. And based on the best found solutions or best found permutations, the pheromones are going to be updated, and this process is going to be continued. But when this algorithm is going to return a permutation, again, the permutation will go through this algorithm too, which converts a given permutation into a feasible permutation. So some results. First, I would like to tell you about test problems. So one problem with kind of newer versions of assembly lines balancing problem is we generally don't have standard test problems. For some problems we have, and that makes everything easier to compare. But for others, when you check the publications, they have their own version. So for this problem, as this is going to be a version of mixed model assembly line balancing problem, we took a standard problem set of that problem, and we converted it into test problems for this problem. In other words, we add setup times, and actually they are added in a way that's in agreement with the literature. And we decide about the precedence graph. And the reason we changed precedence graph because we wanted to be a bit different. So we have 20 problems, and for each problem we have number of operations. Also, we decided to have different levels of workstations. So in 3 levels of workstations, the idea is when you have more workstations, the problem is easier because the algorithm have more opportunities to assign the work. But when you have less workstations, finding a feasible solution is going to be kind of takes more time. So the workstation level 1 is going to be considered harder than workstation level 2 and workstation level 3. So based on the number of operations in each problem, we added a portion of number of operations to add or subtract to the number of stations. For example, for problem 1, 5, 6, 7 stations, but for problem 20, we have 38, 51, 57 stations. So different levels of stations. So in total, we have 120 test problems, and actually we are going to solve 2 versions of this problem. By the way, when we have a mixed model, but the number of model is 1, that's going to be a simple assembly line balancing problem. But when number of models is more than or equal to 2, we are going to have mixed model. So each problem could be solved as a simple assembly line balancing or multi-model assembly line balancing problems. So we have 2 metaheuristics, simulated annealing and ACS. So for each of them, we gave 2 minutes of wall clock, and we run each of them 25 times to find the average solution. We ran MIP Groby solver only once because it's kind of considered as a deterministic approach, but we gave MIP 10 minutes. So, and the idea is MIP is going to struggle if in finding a feasible solution when the time limit is short. Also, there is another distinction. Every time that the computer manages to build the model, the MIP model, it takes about 10 GB of memory. But for the same problem, simulated annealing or ACS only need 1 GB of memory. So another level of efficiency. So a couple of slides to compare the outcome. So what we do, we solve both simple and mixed model. So I'm going to talk first about single assembly line balancing problem, then the plots for multi-model. And what we calculated is percentage deviations. So for a fixed problem, we solve the problem using 3 methods. We find the best out of 3, and then we calculate the difference, the percentage difference from the best found. So as you see, we can solve the problem. Generally, the MIP solver is good for solving the smaller instances, and they can find the best solution. But after some stage, for example, here after problem 8, actually the increasing number of problems means the number of jobs are going to increase. So the problem is going to be harder. So MIP solver couldn't find anything. But you see that ACS and SA, they perform quite well. And for this problem, which is the hardest problem, because this is the workstation level 1, we have less number of stations. So the problem is harder, and simulate annealing kind of outperform and colony optimization. So for workstation level 2, the problem is a bit easier. So we have similar behavior for MIP, but towards the end, ACS is better. And when we have workstation level 3, which means we have the easiest possible version, so nothing to hope about MIP, but the rest is doing okay. So for two model problem, again, with workstation level 1, which is the hardest, again, MIP solver is capable of solving small problems, but we found good solutions. I say good solutions because for these problems, there is not known optimal solution. And for big problem, it's really hard to prove that a particular solution is the optimal solution or not. But they are good feasible solutions. And you see that performance of simulated annealing is generally better than and colony optimization. So for level 2, both algorithms almost the same. Simulated annealing slightly better, and finally they solve most of the problems if they can solve, and their performance is quite good. Okay, so what I presented is our first attempts in solving assembly line balancing problem with straight lines. So we are still working on these problems, and the idea is to be able to solve the base models efficiently, to be able to extend it to bring more and more considerations. So right now I'm working on U-shaped model, and in future we will work on parallel and two-sided version of the problems. Also, not generally sequence-based modeling is considered. We are working on some time-based modeling as well. So some work from modeling side. Possibly that would be a good conversation to have with Alison. And when we are comfortable to have a kind of a solid solver for the base case, we would look at the a bit more complicated problems, kind of considering restricted resources or worker assignment, multi-man, and similar problems. And the stochastic version definitely is going to be something to be tackled in the future. So we have a couple of publications on assembly line balancing, and generally they are based on applying several metaheuristics to solve the problem. And that's all. Thank you for attending and listening, and I'm happy to hear if you have any questions.